All right, Lecture 3, the periodic table. Let's go nuts. So, periodicity. A period is a length of time or space or any other thing you can measure things across. Okay? Um, so, periodicity is the tendency of some property or value to repeat across a period. So, think of an old grandfather clock with a swinging pendulum. The swing of the pendulum repeats across both time and space. Okay, it is very uniform. That's why they use it to measure time. Okay, the periodic table of the elements is an arrangement of the elements in the periodic table such that their chemical properties repeat across the table as a whole. Okay. So, when it came to it, as with everything else in science, it was not the work of a single individual. Science is all about collaboration. Hundreds, thousands, millions of people working together to make these discoveries. So, by the late 19th century, people had been working on different ways of arranging the elements. They couldn't figure out one way that made sense. But a number of people had noticed that the chemical properties had a tendency to repeat. So first off, we have Johann Wolfgang de Bereiner, 1829. He identified triads of elements that had similar chemical properties. For example, lithium, sodium, and potassium. Then, quite a ways later, 30 years later, in fact, we have Alexandre Émile Beguet de Chancourtois. In 1862, he arranged the chemical elements by weight. They had a way of measuring the weights of the individual atoms at that point. What he did then was he took this long strip of paper that had all the elements listed one after the other, and he wrapped it around a pole. And he saw the same thing that Dobereiner did, was that certain elements had similar properties. When he wrapped it around the pole, you'd have one element above the next, above a next, above a next, and they would have similar properties in that way. Okay? He called it the telluric helix. For this, I think a little bit of visual would help. Okay, so you take this long, thin strip of paper, and then you wrap it around a pole. You're going to wrap it in this spiral pattern. That spiral is called technically a helix. It's called the telluric helix, probably because it ended with the element tellurium, is my guess. Don't know that for sure. But you'll see that here, one element above the next, above the next, above the next, going down, that's where you saw the repetition of those chemical properties. Okay. But moving on from Chancourtois, we are going to get Julius Lothar Meyer and William Odling in 1864. So it's really starting to pile up at this point. They noticed further similarities, and they arranged the elements by weight once again, but this time they prioritized a property known as valency. The valency of an element is how many atoms will that atom bond to. So, going back to the page, if you have, so here's your valence. If you have a valence of 1, then this guy will only bond to one other atom. If you have a valency of 2, then he can bond to 2 other atoms, right? So that is what valency is. So Meyer and Odling, they continued with the trend of putting them by weight, but they also put in the valency. Okay? And having done that, they saw that this further chemical property made greater sense. They were adding more details, more nuance to our understanding of the elements and ways to arrange them. So around that same time, the 1860s, we have Englishman John Newland. He noticed periodicity. He also noticed that it tended to repeat in groups of 8 elements. And he called it his rule of octaves, which was unfortunate because people made fun of him. I mean, seriously, at conferences, they would ask him to play songs with the elements. Kind of a dick move and not particularly helpful. But the fact is, he was kind of right, kind of wrong. And it came down to it when we finally got the guy who typically gets the credit for this, Russian Dmitry Mendeleev, in 1869. He published, just before Julius Meyer, a complete periodic table. So he took into account periodicity, that is, the tendency of the properties to repeat. He arranged the elements by weight, but he prioritized chemical properties. He gets priority not only because he published first, but also because he left gaps for undiscovered elements. And when he did that, he correctly predicted the approximate mass and chemical properties of those elements, specifically gallium and germanium, in the middle of the periodic table. He also prioritized chemical properties, and therefore correctly, as we now know, switched elements such as tellurium and iodine. Tellurium, we now know it as element 52, has a weight of 127.6. Iodine is element 53, has a weight of 126.9. So Mendeleev saw that tellurium had the same properties as it had properties that meant that it should be below oxygen. Iodine had properties that meant it should be below chlorine and fluorine. Okay? So therefore, he switched those two elements in the periodic table, knowing enough to know that there was something going on that he didn't yet understand, is why Mendeleev tends to get that priority. So this is another name you're going to want to remember. The names on the previous slide here, I like to point out that science is a matter of lots of people working hard to do these things, that a lot of people will start to approach an idea before we finally hit upon the sort of correct notion. Okay? The result was the periodic table. So let me show you real quick the full periodic table again. This is the modern periodic table with the elements arranged not by weight, but by number. That is to say, how many protons each one has. We'll get into that more in a bit. So 1 and 2. This is where Newland got his rule of octaves. We have these two elements here, lithium and beryllium. Then we have 6 more, so 2 plus 6 is 8. Then 2 plus 6 is 8. That's where he got his rule of octaves. Dobereiner, the first one, his triads, his trios, lithium, sodium, potassium, all in the same column now, beryllium, magnesium, calcium. I think he also had copper, silver, and gold. Then coming over here, I think he had maybe one of these three, I'm not sure. Something, toward the middle here on the right-hand side. So that's where he got his triads from. Just three readily available chemical elements with similar chemical properties. And thus, he was sort of hitting on, this deeper structure in the periodic table. So that is the periodic table. Let us start talking about not just who discovered it, but some of the structure of the table. Okay. So, as I mentioned before, hydrogen can either go here on the left or over here on the right. Hydrogen is weird, like I said, the lightest element. It almost always acts like it goes over here on the right. But on rare occasions, it can fit over here on the left as well. It's, just one of those things. Now, vocab. Bits of vocab you'll need to know. The columns of the periodic table are called groups. So our chemical groups are the things that have the same sorts of chemical properties. Now, the rows of the periodic table are called the periods. So remember, a period is the thing that the stuff repeats. Right? So the row is the period, the column is the group. And the thing that repeats across the period here is chemical properties. So broadly speaking, there are 3 kinds of elements. We have metals on the left, nonmetals on the right, and then in between them we have the semimetals or metalloids. As you can see, the vast majority of the elements out there are metals. Most of the matter is metals. The nonmetals are really, really important to organic chemistry, to life, to biology. And then in between we have the semimetals. And they have properties partway between the metals and the nonmetals, hence the name. Okay, and they form that sort of narrow band right there in the middle. Okay, real quick, the nonmetals form a staircase going from boron here down to astatine right there. Okay, so if you were to draw a line starting at the upper left corner of boron, go down and right and down and right and down and right and down and right, down and right, everything that lies on that line, not on the corner, but directly touching that line, will be a semi-metal, except for polonium and aluminum. Those are just metals. Okay? Everything else on that line will be a semi-metal. So boron, silicon, germanium, arsenic, I'm going to stumble over this a lot. Element 51 is antimony here in the U.S. It's called stibium in Europe. It's something you almost never deal with in freshman or undergraduate chemistry of any kind. When I went to grad school, the professor who I took for my semi-metals class, my semiconductors class, he was Greek, so he always called it stibium. It's stuck. I'm going to stumble over that a lot. I'm sorry. So antimony, tellurium, and astatine. Those are our semi-metals. So you just draw a line forming a staircase going down from top left to lower right. Most periodic a lot, I shouldn't say most, but a lot of periodic tables have that line drawn on there to help you out. That's how you recognize the semi-metals. All right, so metals on the left, non-metals on the right, semi-metals forming a narrow band in between. All right, now, these two red boxes, the far left and the far right, we call those the main group elements, or group A. In the middle, we have the transition elements, or the transition metals, or group B. The group A, group B thing is kind of falling out of favor, as is the main group name. The transition metal name is here to stay because there's so many of them. But it's still useful to know these things. Main group for the left and the right, transition for the middle. You'll notice that there's this box down here. Technically, this long, narrow box with just two rows, it fits in right here. It goes in between the main group elements on the left and the transition metals on the right. So going back over to ptable.com, you can actually see it. They've sort of carved out that little nook right there for the lanthanoids and the actinoids. The reason we do that is because, as it stands, the main group, the transition metals, that adds up to 18 columns. You throw in the rare earth metals, these guys down here, and then suddenly the periodic table is 32 columns long, and it is no longer convenient to fit it on a single sheet of paper. If you pop it out, put it on the bottom, the whole thing fits on a single sheet. It's a lot more convenient. The fact that these guys are all incredibly rare and more than half of this bottom row down here doesn't exist in nature makes it, we might as well just pull it out, set it aside. We don't work with it all that often. All right. So here's our transition metals, main group on the left, main group on the right. Now, you'll notice up at the top that the columns are labeled 1 through 18. Those are the various groups. On older periodic tables, you'll see not just 1 through 18, you'll also see 1A and 2A, group A. And then it'll come over here, 3A, 4A, 5A, 6A, 7A, 8A. So they're distinguishing the main group elements from the transition elements. And then down here, you would have 3B, 4B, 5B, 6B, 7B, 8B, 9B, 10B, 1B, 2B. Nothing is ever simple. You can kind of see why they have started to discard that method of labeling these things. Just go ahead and label the columns 1 through 18, right? You're going to mostly, if you're going to talk about the group, you're probably going to be talking about, the lithium group, the beryllium group, right? But even with that, some of these groups have names, and those names aren't going to be going anywhere. The ones that you are expected to know, The first column on the periodic table, all the way over here on the left, those are the alkali metals. Then over right next to it, the second column, those are the alkaline earth metals. That refers to the fact that they form bases. Sort of. There's a lot of history here. Alkali, alkaline, alkalinity, those are different words referring to bases and the basicity, the baseness of stuff. Okay, and these metals tend to form strong bases. Okay, so alkali metals, first column, alkaline earth metals, second column. Come over here on the right, the furthest right, you have the noble gases. They are too good to react with the lesser elements, darling. They are very, very unreactive. They hold themselves separate, hence noble gases. Then one column to the left of them, you have the halogens. Okay. So those are not the only ones with names. You have the oxygen group are called the chalcogens. The nitrogen group are called the pnictogens, for example. But the ones you are expected to know are the alkali metals, the alkaline earth metals, the noble gases, and the halogens. Okay. Those are the names you are expected to know. All right. So you will have to memorize. From the learning objectives, you'll have to be able to go from name to symbol, symbol to name for some of the elements. Okay. Hint, hint on the test. Hint, hint. Right. So 1A, 2A, 5A, and 8A. So again, popping back over to the periodic table, 1A and 2A, you have to know all of the alkali metals and all of the alkaline earth metals. 5A means the boron group, and 8A means the noble gases. Okay, so you have to know either side of this chunk over here on the right, the boron group and the helium group. And then it says that also wants you to know all of the nonmetals. That's easy enough. There's only 10 of them. Carbon, nitrogen, phosphorus, oxygen, sulfur, selenium, fluorine, chlorine, bromine, and iodine. Okay. And then, boron, aluminum, those are both in group 5A. Then silicon in 10. Those are both directly below carbon, as is lead. So they don't expect you to memorize all of the carbon group, but you have to know several of them. Silicon, tin, and lead. Why do some of the symbols not match? Foreign languages. You just deal with it. Okay. And then finally, you need to know the first row of transition metals and then some of the heavier metals. So the first row of the transition metals is the top row here in the middle. So we're going from scandium all the way over to zinc. Then you need to know silver, gold, mercury, and platinum. And then I believe uranium was also on that list. So silver, platinum, gold, mercury, uranium. Be careful with silver and gold. Okay? Silver is Ag, gold is Al. Okay? So those are the elements you'll need to memorize. Do not try to do this the night before the test. Okay? Make yourself some flashcards and start practicing right away. I promise you, you're dealing with dozens of elements here, dozens of symbols. You are not going to be able to get all of them in a single night. So let's see, 7, 14, then another, that's a 21. You're looking at a couple dozen. This is not an easy task, okay? Me, I don't think I ever sat down to memorize all the elements. Not really. It's just something I picked up over years. You don't have years. You have about a month. Okay, so get cracking on that. And with that, we are done talking about the periodic table. But remember, ptable.com is your friend. It has all the information you could possibly want, really. It has the atomic number. It has the atomic symbol. It has the name of the element, then the atomic mass. Okay? Just all sorts of incredibly useful information. Hell, it has more information than you really want or need, but it also has all the information you will need. Okay? So ptable.com. And with that, we are done with talking about the periodic table for now. Okay? But remember, memorize the elements, memorize those group names. Okay? Metals on the left, non-metals on the right, semi-metals in between. And with that, we're done with this, and I will see you again